My topic is testing statistical hypothesis, a new look with R. So before we discuss and go into details, so we first discuss what is inference, and before discussing inference we shall discuss what is reasoning and what is statistics. Often statistics is termed as a form of inductive reasoning. For example, if in an area, say in a village, the total number of illiterates is sought, one might use the voter list to extract such information. As another example, we can think of a skull, and the problem is to identify whether this belongs to a female or a male. Now what an expert do? An expert compares the findings of this skull with some existing or some collected measurements of the skull, and then identify and gives his expert's opinion. So we get two types of reasoning. The former is called open and the latter is called hypothetical. Now what is open? What is the difference between open and hypothetic reasoning? In hypothetic reasoning, actually there is some hypothesis or preconception, and in all cases we use data as evidences to give the decision. And now let us pass on to inference. So being consistent with these ideas of reasoning, actually inductive reasoning, we can say that statistical inference is some form of inductive reasoning where we learn from data and arrive at a conclusion or decision. Now as we have discussed, what is inference? Inference is the art of learning from the data. Now there are different forms of inference. Actually we have parametric, we are considering parametric inference, and there are three parts: estimation, hypothesis testing and confidence interval estimation. Now in parametric inference, estimation and confidence interval estimation. So what is estimation and confidence interval estimation? In estimation or confidence interval estimation, we do not have any idea about the unknown quantity of interest, but in hypothesis testing we have some preconception or some hypothesis which is known in advance, and based on the data we just update our belief or just judge the difference or the discrepancy of our belief. Now if we look at estimation and confidence interval estimation, we find that these are different forms of open reasoning or open inductive reasoning, but this hypothesis testing part is very consistent with the hypothetic inductive reasoning. Actually in hypothesis testing we have some idea about the population, or there is some unknown quantity, and we have some idea about the unknown quantity, and based on the data or evidence we want to check whether this hypothesis is acceptable or not. So let us consider an example, that is some situation where hypothesis testing is actually needed. The US Environmental Protection Agency set an arsenic maximum contamination level for public water supplies at 0.010 milligram per liter. So being an environmental scientist, it is often of interest to me, or it is often of interest to the scientist, whether the groundwater of some region is drinkable or not. So if the arsenic contamination is more, it cannot be used for drinking purpose, and if it is if this quantity is less, then we can use it for safe drinking. Now here just providing some value that this water contains this much of arsenic is not sufficient here. We have to check whether this water level, the arsenic level in this water is less or not. That is, here the only form of inference is hypothesis testing. Next, as we have already discussed, in any hypothesis testing the main or central idea is a hypothesis. So what is a hypothesis? Actually hypothesis is an assertion about the population or population parameter. Now there are two types of hypothesis. Number one, research hypothesis, or sometimes called alternative hypothesis, and null hypothesis. So, what is research hypothesis? A research hypothesis is an hypothesis which we want to establish, and the null hypothesis is the negation of it. Now, based on the data, we check all these hypotheses and give our decision. So, we formally define a test. A test is a rule to decide whether the null hypothesis is true or false, and obviously this decision is based on the data collected. Since our decision is based on data, there must be some error, that is in any case decision is not free from error. So, let us consider one example. Suppose you went to market and select an item. Now, what are the consequences? You can just buy the item and the item is defective. So, you do not know that the item is defective, but you buy them. Another possibility is that you buy them or you refuse them just considering that this item might be defective. So, these are two errors. Now, in hypothesis testing, this is a decision making process, and in any decision making process there are possibilities of errors. So, in hypothesis testing also we have two kinds of errors. These are error of type 1 and error of type 2. So, this type 1 error is indicating rejecting the true null, and type 2 error reflects the fact that accepting the false null. So, next is how to construct a meaningful test. Actually, test is a rule to give a decision. So, we need to construct a test. Now, what are the different considerations of constructing a test? Since there are two types of errors, and an intuitive idea may be to define a test in such a way that these two types of errors are minimized. So, actually we try to minimize both the possibility of both types of error to find a test. Now, the problem is that simultaneously minimizing both error probabilities is not possible. Actually, it can be shown that these two error probabilities vary in opposite directions. So, intuitively one might consider minimizing a weighted version of these errors, that is a linear combination of these errors. So, for the description of the intuitive test we need some further notations. So, let x1, x2, xn be the observations, the unknown quantity of interest, that is here it is parameter and it is real valued, is indicated by theta, and the joint probability model by fx theta, and our testing problem is theta equal to theta naught, the null hypothesis, against theta equal to theta 1, the alternative hypothesis, and both of these hypotheses are simple. Then we want to minimize this a p1 plus b p2 with positive weights a and b to find a test psi, that is the intuitive test psi. Now, using some routine calculus one can find that this psi equal to 1, actually psi represents the conditional probability of rejecting the null hypothesis. So, this psi equal to 1 if the ratio fx theta 1 divided by fx theta naught exceeds b by a, and it is 0 if it is less than b by a. But the problem is that nothing can be decided on the boundary, that is if this ratio, actually this ratio indicates likelihood ratio. If this likelihood ratio is equal to b by a, nothing can be decided by this intuitive test, and moreover in our hypothesis testing problems we often consider type 1 error as more serious, but in the intuitive test we cannot control type 1 error rate using this type of tests. So, we pass on to our next topic, and we introduce some more notations and some more quantities. Number 1 is size, number 2 power, and then the idea of a most powerful test. Actually consider testing simple null against a simple alternative. Type 1 error probability is termed as size, and 1 minus type 2 error probability gives the probability of the correct decision and hence termed power of the test. Now, why power? Because 1 minus probability type 2 error gives the probability of rejecting the null hypothesis given that the alternative is true. That is, this actually indicates the probability of a correct decision. So, in any case we want that our decision should be true. So, high power indicates that our test taking the correct decision more frequently. Next is the more the power, the better is the test, that is natural. Now, a test giving highest power among all size alpha tests is termed most powerful size alpha test. Now, consider Neyman-Pearson family of tests. So, we have just discussed construction of intuitive tests and noted that intuitive test has no ability to control type 1 error rate. So, we next pass on to Neyman-Pearson family of tests. So, in case of Neyman-Pearson family of tests, we keep P1, that is type 1 error rate, at a level, at a fixed pre-assigned level, and maximize power or equivalently minimize type 2 error. Considering simple versus simple testing simple versus simple hypothesis, the test can be derived as phi equal to 1 if the likelihood ratio exceeds k, and it is 0 if the likelihood ratio is less than k, and this ratio on the boundary is such that the test is of size alpha, that is type 1 error rate is prefixed at alpha. Now, one thing is very interesting, that whether intuitive test or Neyman-Pearson family of test, both of the tests depend on the likelihood ratio, and each test rejects the null hypothesis if the likelihood ratio is larger. So, what is the reason? The reason is that if we just consider discrete distributions, then fx theta 1 indicates probability of observing the sample given theta 1, and similarly fx theta naught gives the probability of observing the sample given theta naught. So, if the probability of observing the data is higher under h1, that is under theta 1, then we might expect the alternative is dominating. So, therefore, we reject the null. This is why all these tests are based on the likelihood ratio. Next is some further concepts. UMP test, unbiasedness. What is UMP test? Actually, for most powerful test, the hypotheses are simple, null hypothesis and simple alternative, but in practice we may have simple versus composite or composite versus composite. So, we need to discuss or introduce some further concepts. So, one of them is UMP test, that is uniformly most powerful test. Consider testing simple versus a composite alternative. If say the composite alternative is the form of a directional hypothesis, that is it is either of the form theta greater than theta naught or theta less than theta naught. If the most powerful test does not depend on the alternative parameter theta 1, then it is UMP. Now, the problem is that often UMP tests do not exist. So, what to do in such cases? So, we next introduce further concept which is called unbiasedness. A test is called unbiased if its power exceeds the size. That is, we can say that since power indicates the probability of correct decision, so we are taking the correct decision more frequently than taking the wrong decision. Now, using this graph, you can see that what is uniformly most powerful unbiased among unbiased tests. Actually, in the left hand side you can see that within S alpha the most powerful, the best test is the most powerful test, and in the right hand side where we have within SU alpha UMP test is the best. Actually, SU alpha indicates the class of all unbiased and size alpha tests. So, we come to the end of the traditional hypothesis testing. Actually, optimal tests have good power properties, but they often do not exist or difficult to obtain, and UMP test beyond the family of regular exponential distributions rarely exist, and moreover if we have multiple parameters then the problem becomes more and more complicated. So, what are the alternatives? The alternative is obviously far from the optimal, but they are just good compromise tests. To go beyond UMP and UMPU test, we need some further concepts. Number one, the likelihood log likelihood function, that is the logarithm of the likelihood function L theta x denoted by, and we consider testing theta equal to theta naught versus theta not equal to theta naught, that is testing simple versus composite alternative, and this composite is of two sided type. Next we define theta hat. Theta hat is nothing but the maximum likelihood estimator for the data, and we assume that this theta hat exists uniquely. Then we define score function, that is the first derivative of the log likelihood function with respect to theta, the observed information, that is the minus of the negative of the second derivative of the log likelihood with respect to theta, and finally expected Fisher information based on n observations, which is defined by I theta, which is nothing but the expected value of the observed information. So with this we shall go further. Now let us consider the holy trinity. Actually beyond UMP and UMPU test, there are so many tests, but these three tests are termed holy trinity. The first one is likelihood ratio test, second one is Wald test, the third one is Rao score test. The likelihood ratio test is nothing but is derived from the likelihood ratio criterion. The Wald test is nothing but the some weighted distance between theta hat and theta naught. Actually theta hat is the ML estimator and theta naught is the hypothesized value, and Rao score test is something different. It is based on the square of the score scaled by the inverse of the Fisher information, and each test rejects the null for a large value of the statistic. So we have some interpretation, we can give interpretation graphically. Now if we consider the graph, we can find that there is unique theta hat n, that is unique MLE, the true value theta naught, and if we consider the left panel, we find that the positions where L theta hat n and L theta naught lies. Now the difference of these two multiplied by some constant is gives you the Euler criterion. Now consider the top panel, there is theta hat n and theta naught. So the distance between theta hat n and theta naught multiplied by some quantity gives you the Wald test statistic, and if we consider the rightmost arrow, we find the slope of the likelihood function, and our score test is based on the slope. Next, what are the properties of these tests? Interestingly, under the null hypothesis, the asymptotic distribution of all these three criterion is chi-square 1, that is chi-square with 1 degrees of freedom, and quite interestingly, for normal distribution with unknown mean but known variance, each of the criterion gives the same value of the statistic. But the problem is that how to compute all these things. Now if we look all these statistics from computational point of view, we find that score test is the easiest to compute, because it does not involve calculation of maximum likelihood estimator, it only depends on the calculating the score, the information, and all this at the value theta naught, that is at the hypothesis value. After defining all such tests, the query for from a practitioner's point of view is that whether large sample or asymptotic distribution holds for how large n, that is for how large n the asymptotic distribution becomes chi-square 1. Next one is whether nominal level is attained, and the third one, since we are considering some test, so the third one is the most important, what is the power of at some alternative. Now how to calculate this, because we have seen that even for standard non-normal alternatives, the criterion, the distribution of the criterion under the null is quite complicated, and to address the queries of practitioners we need some further concepts and further ideas. To answer the first one, we need to use quantile plot, and for the second and third query we introduce the concept of Monte Carlo test. So, what is Monte Carlo test? Actually Monte Carlo test is based on Monte Carlo methods, that is based on IID observations and a replication a large number of times. So, actually the idea is to generate B independent sets of n observations. Actually n is our sample size and capital B is our replication size, and we generate observations under null and under alternative, and we calculate corresponding B test statistics, B values of the test statistics. So, we have B values of the test statistic under H0 and B values of the test statistic under H1. Then the estimated error rate is nothing but the proportion of observations, that is the proportion of statistic values exceeding the upper alpha percentage point of chi-square 1 distribution, and correspondingly the estimated power is nothing but the proportion of statistic values exceeding the upper alpha percentage point of chi-square 1 under alternative. So, let us illustrate the idea using some example. We consider testing the null hypothesis theta equal to 0 versus theta not equal to 0, and our model is Cauchy, and this Cauchy means Cauchy with location parameter theta and scale parameter unity. So, we consider for example Scott test. The Scott test takes this complicated form, and here at 5% level of significance we reject the null if this TS exceeds chi-square 1.05, that is upper 5% point of the chi-square 1 distribution. Now, how to do this? So, for this test we need to check whether the asymptotic distribution is chi-square for moderate n. Second one is whether the nominal level, that is 5% level, is attained for smaller values or for moderate values of n, and to calculate some power values to just judge how good our test is. Now, for this we use an inbuilt package in R which is called Monte Carlo, and compute the Monte Carlo estimates as we have already discussed for different value choices of n, theta and b. So, we start with quantile plot. If we look at the quantile plot, that is the plot of the theoretical values of the chi-square 1 distribution versus the generated the observed quantiles of the generated values under H0, we find that most of the points, that is the circles, lie on the red line. So, this indicates there is some type of difference from the postulated distribution, that is chi-square 1 for n equal to 50. Now, as we increase n from 50 to 100, we find that most of the points lie on the red line. So, therefore, asymptotic distribution as chi-square 1 is just seen to be justified here, and if we increase n further, that is say n equal to 300, we find that only a few points lie outside the red line. So, we can say that the asymptotic chi-square 1 approximation is valid even for n equal to 100. Next we see how good our test performs. So, using the Monte Carlo package of R, we compute power values and type 1 error rate for different values of n and theta. Now, if we look at the table, we find that for n equal to 50, the type 1 error rate is maintained at 5% level. The power becomes 0.99 at theta value 1, but then it decreases to 0, and the same phenomena is observed as we increase n from 50 to 100 and 300. Actually, it can be shown theoretically that as we increase theta, Scott test, the power of such a test, that is power of a test where our alternative is theta not equal to 0 and the model is Cauchy, it goes to 0. So, Monte Carlo methods also satisfy such theoretical requirements. So, these are the observations, that is null distribution of the statistic is close to the chi-square 1 distribution even for n equal to 50. Type 1 error is maintained at the nominal level for n as small as 50. Power first increases to unity and then decreases to 0, and as we have already pointed out that this behavior is justified theoretically. So, finally, with the use of computation, with the use of R, we have obtained the asymptotic distribution of the test statistic under the null. We have also computed type 1 error rate and power at some specified values, and we observed that these power values are in agreement with those as obtained theoretically. These are some references, and finally we note that we have considered only a single parameter, and the statistic becomes complicated if we consider more than a parameter, more than or say multiple parameters, and there are some nuisance parameters. But all these things can be considered in these tests, and we can get further results using some computation methods and programming in R. Thank you.